So today we're learning about univariate analysis, which if I were to summarize it would be this. It's simply describing the characteristics of one variable at a time and using numbers to do so. Okay, now recall the steps of doing quantitative sociological research. Here we are at this stage right here, analyzing the data. We're finally to that. Okay, and you will in the book and on the exercise and by watching my video be employing SPSS on the GSS data set to do some of the measures of central tendency, dispersion, frequency tables, and then later charts and graphs, univariate analysis, in other words, that we'll be talking about here today. So let's get started. We can do univariate analysis in a couple different ways, one of which is by calculating some numbers, so we can do it numerically. And this is when we're talking about things such as measures of central tendency, which you're going to read about or have read about in the chapters. And then also graphically, where we can portray measures of central tendency and other properties of a variable. Okay, there are a number of different variables with the topics behind them, of course, that can be approached by a simple univariate analysis. Like, for example, we're interested in how religious Americans are, or maybe how conservative or liberal they might be, or how they feel about abortion. And of course, since we have general social survey variables or data on these questions, we can measure their univariate characteristics. And again, one of the important ways of doing that is using the proper measure of central tendency for a variable that we have at hand. Now, what's a measure of central tendency? Well, simply it's this. It's a statistical measure that defines the center of a distribution of data points across a range of cases, or if we're talking about the general social survey, how people may have answered on the question of do they support abortion, and how those answers are distributed across all respondents in the survey. The purpose of using a measure of central tendency is to locate the center of the distribution of scores by finding a single measure that represents the entire set, that tells a story, basically. So the goal is to find the average or most typical score for the entire set, just putting that differently. There are three measures of central tendency. There is the mean, the median, and the mode. The mean essentially is just adding the unit values and case values and dividing it by the number of scores. Okay, you learned this long ago. The median is where we take the value that divides the population exactly in half in a single variable, or in other words, the midpoint of a distribution of observed values in a variable, such that there is an equal probability of falling above or below it. Now, and I'll show you some examples of this as well. Okay, and then finally the mode. It's the most frequently occurring value in the distribution of a single variable. Okay, so when do we use the mean? Because there are some rules here in regards to when we use the proper measure of central tendency. We only use the mean when we're analyzing a continuous variable. We don't use it to analyze a variable like sex or race. So if we have like a variable of age, as we do in the GSS, we'd run a statistical mean using our SPSS program, and that would tell us that maybe the average age is 43. I actually think it's higher now, but anyway. And if we had an income variable, which we do, we might find that it averages $32,000 a year. So of course that tells us a story, and maybe that answers, well, a couple of different research questions here. Maybe we're interested in knowing, well, what's the average age of American adults? Well, it would be this. Or what's the average, excuse me, income of Americans at a certain time and point, and maybe it's that. Okay, so just simple statistics, numbers like this help us to answer that kind of question. Now then the mean. Well, going back to the mean here quickly, I said here it's not used for a nominal variable like sex because we don't want to talk about what the average gender is or sex is in a sample, or the average race. It's kind of awkward to talk about it like that. Instead, we would use another measure of central tendency. We might use the median or the mode. The median is used when the mean does not provide a good representative value or where we shouldn't be using the mean. It's most often, I think as your textbook indicates, used when we're dealing with an ordinal variable. And so, again, in the GSS, we have a variable that measures how often people pray, and it goes from never to, I think, once a day or something like that. Around 6 or 7 different possible answers a person can give that are arranged from low to high. And the median ends up being about 3 or about a few times a week. Okay, and that's kind of the way it works out when it's calculated. The mode, on the other hand, this is basically the value, again, that's the most occupied by cases. So if we were to run, if we were to analyze the race variable, what we're going to find, of course, is that whites will constitute the largest category. They'll have the most values, basically meaning that whites are the largest racial group. Or to put it this way, white is the modal category in the race variable. Now, like Babby says in your textbook, using a nice chart here, here's kind of the rules summarized, so to speak. So you really want to use only the mode for nominal level variables, although I'll say that maybe occasionally you could use it for ordinal level variables. Median for ordinal, although sometimes people do in fact employ it for interval level, ratio level variables, or continuous variables, and then the mean for those variables. So by way of example, again, nominal variables like race and sex, we would find the mode for that. Ordinal variables like maybe support for abortion, we maybe would find the median, or prayer frequency or church attendance might be better examples actually. And then interval level ratio variables like age and income, we'd find the mean. Now, nonetheless, let's just, for the sake of illustration, say that we were going to run a mean, median, and mode on a more continuous level variable like age. Okay, and let's say that we have a data set of college students ranging from the age of 18 to 22 years, and we find that in this particular data set there is a bell-shaped distribution. Okay, in other words, there are a small number of 18-year-olds and a small number of 22-year-olds and a large number of 20-year-olds. Okay, and really there would be a nice bar chart here, but we've just kind of flattened it out to make it look like a curve and whatnot. In situations like this, the mean, the median, and the mode will actually approximate one another. Okay, the average is 20, the median is about 20, half of all cases on either side, and then the mode is also at 20. All right, but that's not really a very realistic situation. Instead, if we were to run all three again, which we shouldn't do, but if we were to, for like the age variable from our GSS data set, here's the ages of respondents there from 18 to 88, or 89 rather, the frequency, and this is a histogram chart, FYI. And what we see here is, if we were to calculate the mean, median, and mode, is that they're all pretty much apart from one another, although the mean and the median come pretty close to each other, as it turns out, okay, just by happenstance. But the modal category, I think, is here. And is that 25-year-olds? It's the most occupied category. The mean is about 46-ish, I think, 47-ish, if I'm eyeballing that right. The median is probably about 48, 47, something along those lines. Okay, but again, just for the sake of illustration, we typically use only the mean to describe the distribution in this way for an interval level variable. Okay. There's also measures of variability or measures of dispersion, and these are instruments that we can also use to tell an interesting story about a single variable at a time. Dispersion or variability basically describes the spread of, let's say, respondent scores in a distribution, okay, like how spread out age is around the mean in particular. Okay, small variability or small dispersion means that the scores are all clustered close together. Large variability means that there are large differences. They're all spread out among respondents. There are two common measures that are used typically for interval level, ratio level variables only: the standard deviation and the variance. Now also, sometimes there is used something called the interquartile range, which I believe your textbook mentions. It's a measure of variability, again, based on dividing a population, a data set rather, into quartets, or quartiles rather. Quartiles divide a rank ordinal variable into 4 parts, and the values that divide each part are called the first, second, and third quartiles. And this way we know the numbers or percent of people who fall within in each quartile. But usually when we're trying to describe an ordinal or a nominal variable, we don't really worry about range too much. We just talk about mode and frequencies, as we'll see. Okay. So Just to illustrate this, it's a fuzzy graph. Don't worry about what this measures and the frequency numbers and whatnot. But let's say that we have three different variables. We've overlapped them each other, and each hill or bell-shaped curve here represents the distribution of values across three different variables of people, let's say respondents on a survey. It's possible to have a variable where there's very low variation, where all the people have clustered around a single answer. Maybe it's the middlemost value or the mean. And then maybe there's another variable where there's a moderate amount of variation, where there's some values on getting close to the extremes, and then there's variables with high variation where it's more flat, where there's lots of people at the extreme ends, and then a little bit more in the middle. Okay. So what variables might have low, high, and maybe moderate variation? Okay. Well, income, I think, as we'll see in the GSS, has pretty high variation. It can be pretty low or pretty high, right? From nothing to millions of dollars a year. Age, well, okay, depends on your perspective, I suppose, whether it's high or low. We saw in the histogram, didn't we? If I were to back up really quickly, that looks like a pretty good spread. Maybe that's a moderate variation or dispersion. All right. But of course, if we're just focused on a sample of elderly people, we would see low variation, wouldn't we? Because we define elderly as what, 65 years plus, and there's not many people who live beyond 85 anyway, or 80. So it'd be a very low variation sample. Or if again we were focused just on college students, a low variation. All right. IQ may actually have a high mean. All right, and I say that deliberately, but low variation, especially if we're talking about a college classroom where people tend to be fairly equivalent in terms of their abilities and talents. I mean, you have to have a certain IQ to get into college and a certain ability to do things, right? So in other words, your IQs may be pretty high here in the classroom or offline classroom, but there's low variation, low differences between you. You may dispute me on that, okay? Now, as far as like GPA is concerned, that might be also true. Maybe you have a high GPA so far, but yet there's low variation, especially at the 300 level, where again you're juniors and seniors and you've survived the first 2 years. So again, probably fairly equivalent. So in an intro level class, I just said 170. I'm not sure why I did that. You'd expect a lot of newcomers, people who are fairly green, and their grades won't be doing very well at first anyway. So they may have a low GPA, and there's lots of variation, lots of good students and a lot of poor students too. But we can talk about it kind of in general descriptive terms. Well, the distribution looks like it's got a lot of people on one end and a lot of people on the other end. But there's a more technical and precise way of capturing this idea, and that's where we measure the average distance from the statistical mean. Again, if we're only talking about interval level or ratio level variables. And this measure is useful for getting an idea about how much dispersion there is around that mean. A standard deviation is small when the scores are clustered tightly together around the mean. Like let's say just a sample size of college students, we're looking at age, it's not going to be a much variation there. But it's large when scores are scattered far away from the mean. Like for instance, if we're trying to get a data set together of all Americans between the ages of 0 and 113. So to crack the hood a little bit, this is how the standard deviation is actually calculated. And you may have seen something like this in your statistics class whenever you took that. It may look like a scary equation to some people, but it's really not. Let me try to explain it to you, what the component parts here. What this basically measures is the distance from the means unit score, all right? And so what we have here is x. And x basically is, I say unit here, it could be case is another word, or a respondent score, let's say, on age. All right? And x with the little bar over it, x bar, I'll say, is the statistical mean of everyone's age. Okay, so maybe it's 47, and then your age is 20. Bob's age is 22, and Sally's age is 38. I don't know. So what happens is that each person's score is subtracted from the mean, or the mean subtracted from it. It is squared, and then all respondents' differences from the mean that are squared are summed together, and then they are divided by the number of respondents, units, minus 1, and then the square root of all of that is taken, and we call this the result 1 standard deviation, whatever that number may be. We call it 1 standard deviation is fill in the blank number. Why do we subtract 1 from the n? Well, it's something called Bressel's correction. It's kind of a statistical tool that researchers use for a couple of reasons. Don't worry about it. I'm not going to try to explain that. Okay. But if we were to, again, crack the hood even further and see how SPSS would maybe do this, it would do something like this. We have a data column here, a variable of age. There's 20-year-old, 18-year-old, 22-year-old, Bob, Sally, Jesse, whatever. And it goes down, 1,500 sample maybe. X bar, it's going to take the mean of these numbers, subtract it from each person's age. Okay, and that'll get weird values here and there. This person is obviously over the mean by about 49 years. This person's under the mean by about 17 years, so it's average age 47, just kind of piecing that together. Then they're going to be squared. You may get large numbers here or small numbers and so on. And then that will be summed together and then divided by the number of people. I think I'm saying 10 here. Does that seem right? Or 11 minus 1. And that will give you a standard deviation of 22.11. Okay. So what that tells us, basically, is that the standard deviation is 22.11 years. And the mean is actually 37 years. And so how do I use this? So if I were to analyze the standard deviation, write it up, in other words, what I would say is, what I would do first is take 22 and 11 and subtract it from 37. And that gets me 25-ish, let's say, okay? 15-ish, what am I saying? Okay? And then I will add it also, 22 to 37, and that gets me 59, right? And so I will say that 2/3 of the sample falls between the ages of 15 and 59. All right, that's how the standard deviation works. Don't worry about trying to understand why exactly, but that's what it basically does. It tells us a huge percentage of the sample falls between those two fence posts. So that gives us the idea that the standard deviation is pretty wide-ranging here. There's a large dispersion of scores around the mean. We could have had a standard deviation that was 2. And that would mean that the vast majority of people fall between the ages of what would be 35 and then 39, if we take 2 from 37 and add 2 to 37. So it just gives us kind of those fence posts again, that we know where the majority of the people fall. Not everyone, but the majority. So looking at this example, age from the standard, from the GSS data set, the minimum age is 18, the maximum is 89. So 100% of people fall between 18 and 89, okay? But that's not that interesting. We know the average age is actually 48 here. And it tells us when we have SPSS calculate this all that the standard deviation is 17.304. So to figure out to figure out where the majority of the population falls, where 2/3 of them fall around the mean, we would again take 17.304 from 18.14, and that would give us 31-ish. And then we would add 17 to 48, and that would get us, what, 65? So 2/3 of the population falls between 31 and 65, if again I'm doing my math right quickly, okay? And it's kind of a useful tool. So the standard deviation tells us there's a decent spread, but not a huge one, I suppose. Okay, and just to kind of visualize this graphically, it kind of looks more complicated than it really is. Pretend we have a variable that all the cases on some variable's axis form a nice bell-shaped curve for us and whatnot. The standard deviation, which is a sigma here, one standard deviation is the sigma sign, that's the Greek letter sigma, is basically 30 to put it this way, 34.1% of cases below the mean fall within one standard deviation, and 34.1% of cases above the mean fall within one standard deviation, or 68%. So roughly 2/3 is what I meant. So a good chunk of the population right there within one standard deviation of the mean. And mu right here is the mean, incidentally. Now, in 2 standard deviations, 2 sigma, basically, you add another 13.6% on each side. In 3 standard deviations, 2.1%. Okay? And you're getting pretty much everyone a little bit after that. And here's a slide. You can look at this later that essentially just walks you through what I just did and uses more precise numbers. Okay? So when I want you to talk about the mean and the standard deviation, you would report the mean in words. The mean of age is blah, blah, blah. The standard deviation is blah, blah, blah in years. And it means this. That's what you would report. All right. So what I might ask you to do on an exercise or a quiz, and certainly on the final project, what you're going to do is analyze and interpret a table of data around a single variable or 2 or more variables. All right. So one way we could do univariate analysis, okay, is by simply, again, reporting at least these numbers, the average and then the standard deviation. You just report them. The average age is 48.14 years. The standard deviation is 17.304 years. Boom. That's pretty much all you have to say. You could mention the minimum and the maximum, but it's really not that interesting again. And the n, not that interesting. But there's also a second part, though. Not just analysis. We actually need to interpret. And this is where we take a step back, look at our numbers, and then inform the reader in writing about whether or not our finding supports our hypothesis and, by extension, our theory. And then maybe reformulating the theory if we need to, or just recapitulating it and summarizing it again. We would explain what I found, back to theory, why the theory is supported, or why the numbers seem to support the theory. And then also, critically, what are the flaws of my analysis? So this is what I would do if I were writing this up, and you should do likewise. The average age is 40.14 years. The standard deviation is 17.3 years, which tells us that 68% of American adults fall within 31 and 65 years of age, roughly. Okay, I did round up there. My interpretation is, my hypothesis is supported that most Americans are middle-aged and most fall about 9 years below 40 and about at retirement age. I'm really talking about the range there, kind of roughly. All right, so I didn't really mention this at first, but let's say I had hypothesized that the average age of American adults is middle-aged and not young, college age, let's say, or elderly, because there was a large baby boom in 40-something years ago, and that should lead to a large number of people averaging out the age at that. I don't know. Probably you could come up with a better theory or explain it better than I just simply did off the cuff like that. And then I go and I say, well, the age structure is likely because the fertility rate has decreased over time. Yeah. And life expectancy has increased. Okay, sure, you could also say that. This is where you have to take a step back and think more theoretically about why it is the numbers are that they are. Okay. And then I would say a criticism here that, well, there's not much to say, is there? This analysis doesn't tell us much about the cultural situation of the United States. And importantly here, when we're just analyzing one variable at a time, it really doesn't tell us, well, what correlates with that variable or what causes that variable, right? But we can start talking in language like that, correlation and causation, when we start doing bivariate analysis later on. So, but of course, this is not the only tool that we could use when doing an analysis and interpretation of a single variable. We could also produce what's known as a frequency table. All right, and SPSS will allow us to do that, and you'll have to do that in a few exercises here and there. All right. Let's say we have a topic race we're interested in, a research question. What race are most Americans? Yeah, I know it's pretty dumb research question. And our hypothesis is most Americans are white, and there's a theory behind that. You know, country formed by European people. Okay, well, mostly going to be white. All right, but just run with me. It's just an example for educational purposes. So what we could do is produce a frequency table using the single variable. Now, as we, well, actually, we may not have seen an example of, well, maybe as I showed you in one of the videos about how to do things, or I will anyway. The race variable in the GSS, there are three possible options. Not the best, but the question was something along the lines of what race do you consider yourself, white, black, or other, okay? There are like four categories here, or columns rather here, that we want to pay attention to. There's frequency, the number of people in the sample out of 1,500 who answered of the three categories. The percent of people who answered of all the possible answers. And then there's a thing here that's going to look identical in this case called the valid percent that will give us the percentage of people who only answered valid responses. Okay, and what that means is, as we'll see in other variables, some variables will give us three other categories than just the proper responses, things like IAP, DK, and NA, and they'll usually label them 0, 8, and 9. Okay, what does that mean? It means inapplicable, don't know, and no answer. We'll see that when we talk about more opinion and attitude questions, like on abortion. There's some people who are like, I don't know, and I don't want to answer that, and I don't think it's applicable to me. But here, of course, most people in our culture will identify as some kind of race. 100% of people answered that they were some kind of race, right? So anyway, the valid percent is always the column we want to use because it will exclude the don't knows, not applicables, or no answers and inapplicables. All right. The percent column will include all those missing answers. We call those missing values, the don't knows and applicables and no answers. Cumulative percent is, well, just that. There's 76% of whites, but you add blacks to that pile, it makes it 90%, and then you add the other, well, that's 100%. But we rarely use that for any major reason. So how would I write this up in an analysis and interpretation? Well, I would say this, probably 76% of adults are white, 14.5% are black, and 9.5% are other, right? Using the valid percent, only the valid percent column. Interpretation, most adults are white, with a minority as black, and then at least one other race. Okay, and I would say that my hypothesis is supported that most adults are white. I probably should have typed it in right there. And then I would say, back to theory, this is because most historical immigration was from Europe. Okay. And then I might say, of course, these data are for adults and do not include children under age 18. I'm criticizing what I just did. Also, we need finer distinctions in the other category for more refined conclusions about other research questions, something like that. Here's another example of a frequency table produced in SPSS, as you will see. And here's yet, well, sex, of course. Notice again, there's no missing cases. Here's yet another one. This is religion. There are 13 different answers a person could have given. And notice here that there's going to be a slight difference in the percent and the valid percent columns because there is, looks like a total of 5 people who gave no answer, and it's labeled as missing by the researchers. And so that constitutes 0.3% of the full range of people who answered. And in the valid percent column, they are excluded. So we'd use that in doing our analyses. Okay. Another example of a frequency table. This is the frequency table of a interval level variable. Okay, or rather ratio level variable, I suppose, because it has a 0. Yeah, I think that would be right. How many hours of TV watching do you do a day? 0 up to 24. Okay, we do have people who said it's not applicable, they don't know, and 34% of them. Okay, and then 0.3%. So we excluded 34%. That's really something, actually. Okay, a third of the people. But it looks like those people who answered, their responses range from a modal category of 27% all the way down to a very low 0.1%, I think. But anyway, the point is that you never want to do this. A frequency table is not really appropriate for a variable with a large number of cases. What if we did this for age, or worse yet, income? Then the table would spill off the page, it'd be hard to read, and would you want to report every single category's numbers here? No, you don't want to do that. Instead, of course, what you would rather do is just talk about the statistical mean and the standard deviation and analyze and interpret those. All right, so frequency tables used only for ordinal level and nominal level variables. And moving on to our next topic, charts and graphs, this also is generally true for using charts and graphs, okay, as we'll see, pie charts and bar charts. But there are some graphs, charts that we can use for continuous level, that is, interval level and ratio level variables, because it will also help us tell a straightforward story, okay? Now, as Alan indicates in a table in the textbook, Babby, there are some rules of thumb regarding what kind of variables you should use for specific kinds of charts. Generally speaking, discrete, by which they mean nominal and ordinal level variables, you should only use with bar and pie charts. And then interval level or ratio level variables, otherwise known as continuous, you should only use with histogram and line charts. Okay. And here are a few examples from the General Social Survey of those kinds of variables, for what it's worth, all right? First, a bar graph, of course. We have a hypothesis, maybe. We think a majority of American adults are conservative, ranges from extremely liberal to extremely conservative. We could report the modal category, which would be moderates here, all right? It might be the median might be calculated in that range to 1, 2, 3, 4, perhaps as well, looks like. And a bar chart will help us get an idea on just how large that moderate category is relative to all the others. Okay, so it can help us tell a story. Maybe I'd analyze it something like this, including the mode. The modal category is moderate with about 40%, followed by 20 by conservative at less than 20%, and slightly conservative versus liberal about 12% each. The other are smaller categories. I might go on and talk about those, report those numbers maybe. The interpretation is that almost a plurality of adults are moderates and only about 20% are conservative. This does not support our hypothesis, if you remember. So the majority are conservative. I don't think that supports that. Maybe this is because the population is becoming more educated and more exposed to media influences, and this may have a tendency to liberalize people. Also, the population is becoming more diverse as well, and so on. There's several theories you could mention. Yet, however, it's not clear what the distinctions are between slightly and then full conservative versus liberal or even extremely so. And so that kind of obfuscates maybe some of our interpretation. And in the chapter, you'll learn how to produce a pie graph. This is for political party affiliation. And again, really only useful for variables that have a few categories. This one's kind of stretching that, I think, almost to the breaking point. If you had probably more than 10 different categories in a variable, it'd be kind of hard to compare pie wedges. But this will, of course, give you the idea on just how much of a piece of the pie one category is relative to the others. Here there's they're fairly equal in distribution, so I'm not even sure I would actually use a pie graph to analyze and interpret political party affiliation. Really, I'd probably fall back on the frequency table. I feel like that might be a little bit more useful. But anyway, I would analyze and then interpret it in this way. Report the numbers, talk about how my hypothesis was not supported, and then maybe explain why, and then criticize the data here and what I've done. Now, for interval or ratio level variables, we don't want to use a pie chart and a bar chart because then there's too many pie wedges and bars, and it would be a hot mess. Having said that, as the book teaches you, we're going to use a histogram. So we'll do that, and you'll want to produce that for whatever variables necessary. We have a hypothesis here. The average American adult is middle-aged, okay? And when you produce a histogram, which looks an awful lot like a bar chart compressed together, it'll just show you simply what the shape looks like or the distribution across the age range of 18 to 89 plus. It'll give you a sense as to, where the bulk and the peaks are of the population. There's almost kind of two waves, isn't there? There's a cluster of people underneath the age of 42, and there's kind of a cluster of people between the ages of 50 and looks like 70, and then there's a huge drop off after that as mortality really begins to kick in. Histograms at the same time the SPSS produces them will generate the statistical mean, the standard deviation, and the number of people who answered the question, which is kind of useful so you can use these numbers to analyze and interpret them in a way that we did earlier. Okay, this means standard deviation is slightly different because this is a slightly different sample. Another graph you can use for an interval level or ratio level variable is a line graph. Here we have income, and it's got several different categories. This is actually almost like a glorified ordinal, but we're calling it a scale variable. And it looks like there aren't that many people who make less than $20,000 and $25,000 a year, and then there's a huge peak in that. I'm not sure how useful this graph is for this particular variable, but it's just to illustrate the point. So now, just as a broader point to make, though, and we won't be doing this with our data because we're only looking at GSS data at one point in time, a snapshot. But in fact, we could take all the general social survey questions data that have been done since the early 1970s to 2000 and compare them, and we could create a nice line graph even using simple yes and no, kind of nominal or ordinal level questions from the GSS. And that's what line graphs are typically the best used for whenever you have multiple different data points across a large time frame. It gives you an idea as to how trends are changing and whether they're going up and down. This one I just kind of thought was interesting. The percent of people who favor laws against racial intermarriage, non-black respondents, all years, people who said yes, we should ban interracial marriage. There's a pretty high number of them in the 70s. Holy shit, about 35%. It actually went up a little bit a couple of years later, but then boom, began to plummet, going up. It fits and starts, and then collapsing to maybe 10%, which I'm surprised it's even that high. Okay, the hypothesis was that support for laws against interracial marriage is decreasing in the United States. That seems to be borne out, actually, looking at this. But anyway, we're not going to be doing this kind of time trend analysis. But I wanted to point it out to you, if it's not obvious from other things you've learned about, that line graphs are very useful for comparing percentages changes across time.